In this video, we'll discuss predicates and quantifiers. First, let's take a look at where we are in building the foundations that we need for writing proofs. So, at the base of our foundation are any assumptions that we take for granted, and we'll call those axioms. Then, we've already discussed propositional logic, and recall that propositions are statements that we can determine as true or false. Now, we've been working on predicate logic. So the difference between predicates and propositions is that predicates are statements with variables, and we can't tell whether they're true or false until we set specific values to the variables. So propositional logic is what we use to determine the truth of a proposition, and then predicate logic is what we use in order to tell if a proposition is true if we assign specific values to the variables in a statement. And now we had just discussed the rules of inference, and that's how we can use statements to construct arguments that are valid. So we're starting to show how we can use propositional logic and now predicate logic and the rules of inference and equivalences to start constructing arguments. But first, let's be more specific and discuss what a predicate is. A predicate is a statement with at least one variable that is a proposition when we give specific values for each of the variables. So that means we can determine whether it is true or false when we assign specific values to the variables, and we have to specify the variables are from a specific universe of possible values. So let's look at a concrete example of predicates, and the first predicate that we'll consider is called is power of 2. The universe of the variables for these predicates in these examples are going to be the non-negative integers. So that's going to be the universe of variables. Okay, so is power of 2 is the predicate that says, does n equal 2 to the k for some non-negative integer k? Now, we can't say whether n is equal to 2 to the k for some non-negative integer k unless we know what n is. So we can't say if that's a true or false statement. Actually, it's just not determined because we just don't know. So once we assign a value of n, a specific value of n, then that predicate becomes a statement that we can determine whether it's true or false. So is power of 2 1 means if we set n equals to 1, does 1 equal power of 2? And we can say yes, because 2 to the 0 equals 1. So that predicate is power of 2 1 is equal to true because 1 equals 2 to the 0. Now let's consider is power of 2 8. Well, 8 is equal to 2 to the 3. So that means 8 equals 2 to the k for some non-negative integer k. So is power of 2 8 is also true. So these are both examples of when these predicates are true. But now, if we consider is power of 2 6, we know that this is false because 6 is equal to 2 times 3. So it is not a power of 2. It does not equal to 2 to the k for some integer k. So for is power of 2 6, the predicate is false. Now, let's consider what happens for another predicate, and this predicate is prime, and we're given an integer n, so it says n is prime. So the predicate is prime, n is going to be true if and only if n is prime. And just seeing the predicate n is prime, we can't determine whether it is true or false unless we give a specific value for n. And then we can tell whether a proposition is true or false for that predicate. So is prime 15 is asking if 15 is prime, and 15 equals 3 times 5, so no, it is not prime. So this predicate, when n is equal to 15, is false. However, if we check the predicate is prime 7, when n is equal to 7, 7 is prime, so this predicate is true. So we can think of predicates as statements with variables that we cannot determine whether they are true or false until we consider a specific value for the variable. We can combine predicates with quantifiers. So the first quantifier that we'll consider is the universal quantifier. That's for all or for any. Now it looks like an upside down A almost. So when we combine the universal quantifier with the predicates, we create statements such as for all x in S, which is some set, the predicate holds. And you'll notice that here, this P of x is we're passing in the values in this set x into the predicate. So that's basically we're taking all the variables values for x in this set x, and we would be checking if the condition holds for those specific values. The conditions for the predicate holds for all of those specific values. So it's saying for any x in the set S, the predicate P of x holds. So let's look at how we can consider an example of a statement. So one statement that we would translate into first order logic or quantificational logic, predicate logic, is for any integer n is greater than or equal to 2 and is prime. Now the first part, so the universal quantifier is that for any, and we're using the variable n, and our set is going to be integers. So that's for any integer, that's where we just translate it there. We are going to have our predicate as actually two conditions. So the first is n is greater than or equal to 2 and is prime. And this is the same as before, it's just checking if n is a prime number. Now this turns out to be a not true statement, a false statement, and we can see this, for example, if we give a specific value for n. So what happens if n is equal to 15? Well, we see that 15 is an integer. 15 is greater than 2, and we have to check this next condition with 15. 15 is not prime, so that means this entire statement is not true. So 15 is greater than 2, but 15 is not prime. So this predicate, and I'll just highlight it now, this predicate is false because 15 is not prime. So that's why this entire statement is false, because it says for any integer, the integer n is greater than 2 and it's prime, but we just found an integer greater than 2 that isn't prime. So we would call this a counterexample to the statement. But the key takeaway is that when we have the universal quantifier, it's saying that for any element in this set X, the predicate must hold. Now, sometimes it's helpful to think about universal quantifiers in terms of coding. So it's saying when we're using a universal quantifier for any, for all, it's saying for all X in S, this predicate holds. So now let's think of how we would code this up in terms of pseudocode. If you had to write a function or a little snippet of code to check for the condition or the statement of a universal quantifier, and we're going to just assume for this case that as the set, the universe for X is finite, we can write essentially a for loop to check this, and we'll write some pseudocode now. So what we're going to do is that for any element X in our universe of S, we have to check if the predicate is true or not. And the only time we know that this statement with a universal quantifier will be false is the second we find any element in S such that the predicate is false. So that means if the predicate on this value X that we're checking is false, so if we negate that, we should return false. And when we find such an element in that set S, that means we have just found a counterexample, just as we did with 15. And the first counterexample is sufficient to show that that statement is false. And then if we go through the entire set of elements in S and the predicate holds for all of them, then we know that the statement with the universal quantifier is true, so we can return true. So this little snippet of pseudocode is meant to build intuition about how do I check whether a statement with the universal quantifier is true or not. Well, you go through the entire universe of elements from which the predicate variable are specified, and you check. And if you find one element that does not have the predicate true for it, then you return false. That's the counterexample. Otherwise, we return true. The other quantifier that we'll be working with is the existential quantifier. So this is read as there exists, and it looks like a backwards E. And the way that we read statements using the existential quantifier is there exists an element X in S such that P of X holds, that a predicate X holds. And you can think of S again as the universe for the variables of the predicates. So let's look at a concrete example now. There exists an integer n greater than or equal to 2 that is prime. And we've translated now. So there exists an integer n, so n is in Z. Then our universe for the variable for this predicate is going to be the integers, such that n is greater than or equal to 2 and is prime. This is our predicate. And in order to show that the statement using an existential quantifier is true, we need only find one element in this set S. In this specific case, we only have to find one integer for which the predicate holds. So let's consider this. Let n equal 3. Now, when n is equal to 3, I know that 3 is greater than or equal to 2, so that's true. And 3 is prime. So when I can verify that 3 is greater than or equal to 2 and 3 is prime, I know that this entire statement is true, because with an existential quantifier, I need to only find one value in the universe of variables for that predicate for which the predicate is true. Now let's consider how we would code this up now. How would you check if a statement using an existential quantifier is true? So we have there exists an element x in the universe of variables for this predicate such that the predicate is true. So once again, we can use a for loop, and we're going to check all of the elements in S. So for all of the elements in S, and again, just assume for the sake of this that S is finite, we just need to check if any values in that set are such that the predicate is true. So if there's an element in X such that the predicate is true, we can return true immediately, as we just did with 3 in the previous example. Otherwise, if we go through the entire set S and we don't find a single value for which the predicate is true, we have to return false. So hopefully this also builds a little bit of intuition in the relationship between existential quantifiers and universal quantifiers, and see how they are contrast with each other. Now let's practice using quantifiers, and now we're going to express predicates that we had seen before more formally using quantifiers. So here we have the predicate is prime, and the other predicate we'll consider is power 2. So we expressed them in words before, but now we can express them using quantifiers. So let's assume that our universe in both of these cases, our universe for n will be the non-negative, well in this case positive, we'll just make it positive integers. So how can I express is prime n? Using quantifiers, well, I can express this as n, and as just to refresh your memory from before, an integer n is prime if and only if it's greater than or equal to 2, and its only divisors are 1 itself. So that's n greater than or equal to 2, and now we have to express that its only divisors are 1 and self. So we can use modulo if we want, or we can just also just use the symbol for divide. So we can say d divides n means that when I divide n by d, there's no remainder. So you might be familiar with programming where we would say this is n mod d equal 0 is another way to think of it. But now the way that we would express this in using predicates is that for any integer in the positive integer, so any integer, d divides n implies that d is equal to 1 or d is equal to n. And that just means that if d divides n, it has to be 1 or itself. That's just expressing what we mean for the number to have its only divisors be 1 or itself. So that's how we can express the predicate is prime in terms of quantifiers. Now, for is power of 2, once again, we will consider the universe for n to be the positive integers, and then we can express is power of 2 to be that there exists a k, and k would be in the non-negative integers, such that n is equal to 2 to the k. And we were using these ideas before, but we just hadn't introduced the quantifiers. So here we're using the universal quantifier, and here we are using the existential quantifier. And as a good exercise, you can think about how this statement is true and look at specific numbers to see when you will have the statement true or false using the universal quantifier and then using the existential quantifier. And something else to think about is, how can you think of expressing a condition for when a universal quantifier holds, that such a statement holds, in terms of a conjunction of the predicates, and existential quantifier in terms of a disjunction of the predicates over the universe of the variables?